Hi, Bob. What's up?
Hey, Dave. I was just down by the number 4 boiler. The operator's having a problem with the feed water control system. You're probably going to be getting a call in a minute, or maybe in a work order.
Okay, thanks. Now, Bob's one of the instrument technicians here in the shop, and that control system he's talking about is a pneumatic instrument system. It's a 3-element feed water control system. You may be familiar with it already. Now, in a minute, I'll be getting some notification of the problem, and I'll have to select one of the technicians to take care of the problem. Now, as an instrument technician, I'm sure that you'll be selected to take care of similar problems in instrument systems in your plant. Now, the procedure you'll have to go through to locate and correct problems in instrument systems is known as troubleshooting. And it'll be the most challenging part of your job, requiring the greatest amount of skill. But you know, to be able to troubleshoot an instrument system, you have to understand the principles of troubleshooting. So in this program, we're going to be looking at these principles and how to apply them to troubleshooting pneumatic instrument systems. Well, let's begin by taking a look at what troubleshooting is all about. In practical terms, troubleshooting is the process of locating and correcting problems in plant systems. But effective troubleshooting involves more than simply fixing things. It involves a way of thinking, of following a logical procedure to solve problems rather than using a hit-or-miss approach that may waste a lot of time. In other words, the purpose of troubleshooting is to locate and correct problems in a minimum amount of time. So suppose your supervisor or foreman handed you a work order, or suppose he just walked over and asked you to troubleshoot a system problem. Well, where would you start? And what kinds of information would you need? Well, you'd start with the information that was available. If the problem was in a critical instrument system, your foreman might simply get a phone call and you'd have to head out to the plant, taking your knowledge of the system, the tools that you think you'd need, and any information on the system that you might have. But at other times, you might be handed some kind of written notification of the problem, which I'll call a work order. Now, a work order usually contains several important pieces of information. For example, this particular work order tells you who noticed the problem and submitted the work order, when the work order was written up, what system the problem is located in, and a brief description of what the problem is. The person who's submitting the work order, usually a system operator, may not know exactly what the problem is, but he's probably got a good idea as to the general nature of the problem. In other words, from the information on the work order, you might be able to tell whether you've got a rather simple problem like a bad gauge or a more complicated problem like a control system that won't control a particular process variable. So once you've been notified of the problem, you're ready to begin troubleshooting. Well, how do you go about it? Well, let's take a look now at a procedure that you can use to troubleshoot problems in instrument systems. Now, the first thing you've got to do is to prepare. Before you can figure out what's wrong with the system, you've got to know how it's supposed to work. Now, you won't be expected to have all of the systems in your plant memorized or to know everything about them, but by preparing, you familiarize yourself with the normal operating conditions of the system. And the key to doing that is to know where to get information about the system you're going to be working on. You'll find the information you need in the documents you've got in your shop, such as P&IDs, control logic diagrams, and plant data books. And the types of documents you study depend on the types of information you're looking for. Now, let's take a look at several of these documents and see how they can be used to help you familiarize yourself with the system. They're often diagrams that show where the major pieces of equipment are physically located in the plant. A P&ID, or piping and instrumentation diagram, shows the relationship between the equipment in a system and the instruments associated with that equipment. In other words, it shows how all of the equipment in a particular system is connected. Now, another source of information that's often a lot of help is a control logic diagram. It shows the progression of control signals through the control instruments in a system. It usually starts with the first element in a system, the primary measuring element, and continues through to the last element, usually the final control element. Using a combination of P and IDs and control logic diagrams helps you to get an idea of the instrumentation contained in a particular system so that you can locate the problem. Another useful source of information is a plant data book. A plant data book contains the operating parameters or specifications of a plant's systems. For example, it'll tell you how the individual components in a system are rated, what the system is designed to do, and how it operates. It also comes in handy when you're working on a system that's less common, more complicated, or one that you haven't worked on before. You know, your own personal notes are a valuable source of information. As a matter of fact, here's the notebook that I used to use when I was working as a field technician. And by keeping your own personal notes, you'll have a record of specific information about a system that you need to know. When you're out of the shop and in the field and you run across a system problem, your notes could come in quite handy. Now, keep in mind, though, that your notes don't take the place of the plant data books and other documents in the shop. Now, once you've been able to narrow a problem down to a particular instrument, you'll be able to use the manufacturer's instrument service manual, which contains information on that specific instrument. Now, here's an example of a service manual. It contains a number of important sections, such as how the instrument operates, how to install and remove it, and a parts list. It often contains a section on troubleshooting that may include a troubleshooting procedure. A troubleshooting procedure is a detailed set of steps that you can use to locate and correct a problem in that particular instrument. And finally, there's also equipment history records. Now, equipment history records tell you what kinds of problems, if any, the equipment has had before and what's been done to repair it. Now, from what you've been able to learn about the system by studying these plant documents, you'll be able to get a general idea of the tools you'll need to take with you. Halfway across the plant isn't the time to remember that you should have brought along that extra tool. By taking a few extra minutes to prepare, you'll be able to save yourself an unnecessary trip back to the shop. And we've been able to see then that in troubleshooting instrument systems, you'll first be notified of the problem by having your foreman tell you about it, or by receiving some kind of written notification like a work order. Then to begin troubleshooting, you start by preparing. You familiarize yourself with the normal operating conditions of the system. Once you've prepared, you'll be ready to move on to the next part of the troubleshooting procedure, to observe this system. In other words, you'll be prepared to go out and actually take a look at the system's indications. In just a minute, we're going to take a look at the rest of the troubleshooting procedure, but before we do, take time to read over the material in your text and have your instructor explain anything you don't understand. As you've seen, a good procedure for troubleshooting problems in instrument systems begins by preparing. And by preparing, you're able to familiarize yourself with the normal operating conditions of the system. This involves going through the various plant documents, like P and IDs and control logic diagrams. Now, once you're prepared, you're ready to work your way through the rest of the troubleshooting procedure. Now, at this point, you're ready to make a few observations about the system. Now, the purpose of making observations is to identify possible causes of the problem. And in doing so, be objective. In other words, don't be too eager to jump to conclusions as to the cause of the problem. One of the most important things you'll want to do is talk to the operator. The operator will be familiar with the system you're working on and its indications. He's been keeping track of what's been going on in the system and can provide you with information that you won't have been able to find in the prints and the manuals in the shop. such as how the system had been operating just before the problem occurred, and what happened when the problem actually did occur. While you were studying the various plant documents in the shop, you were able to learn about what the system's designed to do and how it's supposed to operate normally. Well, now see if you can find out from the operator what the abnormal operating conditions are. Ask him, for example, whether he noticed anything unusual or peculiar about the operation of the system. Find out from him if the problem started while the process was steady or whether it was being increased or decreased. If the operator on duty is the person who reported the problem, ask him how he first became aware of the problem. Find out whether an alarm had gone off or whether he just happened to observe the problem while he was checking his indications. See if the operator can also tell you whether the problem is a continuous one or whether it's intermittent, and whether he had to put the system in manual. Now, all of these are the kinds of questions that you can ask the operator. That will give you clues as to the nature of the problem. And while you're talking with the operator, observe the system's indications. Now, from your knowledge of the plant, the prints, and your talk with the operator, take a look at the indications on the instrument panel. Check out the alarms, the gauges, the recorders, anything that'll give you a visual indication of how the system's operating, so that you'll be able to recognize as many of the symptoms of the problem as you can. And sometimes you'll be able to recognize the problem while you're looking for symptoms, but other times you won't until after you've finished observing all of the indications and have analyzed the symptoms together. If there are any indications in the field, don't forget to observe those as well. See what kind of indications you come up with there and compare them with the indications you have observed on the control panel. After you've finished observing the system, you'll need to diagnose the problem. In other words, you try to identify what instrument, piece of equipment, or section in the system would most likely be causing the problem. Pin it down to a specific part of the system if you can. Diagnosing the problem is the first place in the troubleshooting procedure where you're going to have to make a logical conclusion about what the most probable cause of the problem is. The more you rely on a logical procedure to guide your thinking, the better the odds are that you'll diagnose the problem correctly. And to a large extent, your skills as a troubleshooter are going to depend on how well you're able to diagnose the problem. There are several important methods you can use to diagnose a problem. One of the ways of doing this is by looking at an instrument's inputs and outputs. If you know the value of the input and the output is not correct, you'll know you've got an abnormal operating condition, and you'll know that you've got a problem. So knowing what the normal operating conditions should be and how to determine them can be critical to your being able to locate the problem. Now, another way to diagnose a problem is to place the system in manual and compare the way the system operates with the way it operates in automatic. You can do this by checking the system's visual indications, such as looking at gauges and recorders and so on. Then, if possible, you may want to duplicate the conditions under which the problem occurred to see what happened. Another method for diagnosing the problem is to find out what the abnormal conditions have in common with each other. For example, if the symptoms of the problem all occur in the transmitter loop, or in the instruments that receive their signals from the output of the controller, then these are facts that can help you narrow down the location of the problem and make a correct diagnosis. After you've made your diagnosis, isolating the problem to a specific instrument, you'll need to make tests to confirm your diagnosis. To do this, you should first notify the operator on duty that you're going to be working on the system. Let him know what instrument you're going to be testing, and if necessary, have him place it in manual for you so that you can work on the system without affecting the process. Then make a visual inspection of the instrument for any obvious problems. For example, make sure the instrument air supply hasn't been shut off. Check to see whether the instrument's been damaged, and inspect it for worn or broken parts. If a visual inspection fails to turn up any obvious causes for the problem, you'll have to make some special tests. To test an instrument, you apply a known input to the instrument and check to see whether its output is correct or not. Each time you make a test, you'll be able to evaluate the results and compare them with the observations you've already made. Now, this should help you to confirm your diagnosis and locate the most probable cause of the problem. If, when you're testing the instrument, you discover that it has a problem, you'll need to figure out whether the problem is that the instrument is actually damaged in some way or just out of adjustment. Because parts wear and age, causing the instrument settings to change, calibration adjustments can change with time. If the instrument's simply out of adjustment, you'll need a calibration standard to provide you with some means of applying a known input to the instrument. Now, with a known input, you can then adjust the instrument until you've got the right output. Now, once you've diagnosed the problem and have made tests to verify your diagnosis, you can be sure you've located a cause of the problem. What you've got to do next is repair the problem. The repair work can be done either right there where the instrument's located or back in the instrument shop, where the repair job's done. Depends on the type of repair that's got to be done. More complicated repairs often have to be done in the shop. Sometimes the environment the work's got to be done in is another factor. For repairs that have to be done under unfavorable conditions, it's usually more efficient and safer to do the work in the shop. If you're not sure where the instrument should be repaired, check the instrument service manual. By reading up on the type of repair work that's involved, you'll be able to get a feel for whether or not you'll have to take it back to the shop. In either event, you'll have to determine the most efficient way to solve the problem. Suppose then that you do have to repair the instrument in the shop. You'll have to remove it first. Now, there aren't any hard and fast rules for removing an instrument from service, since it depends on the instrument and the type of process. But there is one thing that you've got to keep in mind. If the instrument is an integral part of the control system, make sure the system's in manual before you remove the instrument. Make sure you check with the operator to see if it's all right with him. Depending on the instrument and the system, the repair of an instrument could keep the operator busy at the panel controlling the system manually for several hours. You'll have to make sure the system can stay in manual for the length of time you'll need to repair it. After you've removed and repaired the instrument, you need to calibrate it to be sure that it performs properly. Then you need to reinstall it and restore it to service. You should check the instrument service manual for guidelines on how to reinstall it and restore it to service. As you reinstall the instrument, reconnect the supply lines carefully so that you don't cross-thread the connections. Depending on the instrument, you may need to use pipe compounds, sealants, or other protective coatings. Then, once everything is hooked up, open the valve slowly. If you're not careful, you'll apply too much pressure to the instrument too fast, and you could damage it and have to take it right back to the shop again. After the instrument is restored to service, check to make sure that the instrument is working properly in manual. There shouldn't be any leaks or other obvious problems. Then have the operator place the system in automatic and check to make sure it works properly. Now, once you've restored the instrument to service, you also need to make sure there aren't any other problems in the system. Sometimes a problem can be due to one or more causes. You may fix one of them, but you have to make sure there aren't any others. And if there are, you'll have to troubleshoot each problem one at a time using the troubleshooting procedure. Now, the last part of the troubleshooting procedure is to document the problem. Record what you've done to repair the instrument. Fill out the necessary forms and make entries in the appropriate records. For example, if you calibrated an instrument, make sure you update the instrument's calibration record. Now, nobody likes doing paperwork, but documenting the problem may help you or other technicians to solve any future problems that may occur in the system. As an instrument technician, you're going to find yourself doing a lot of troubleshooting. You'll be working on different kinds of instrument systems, and you'll probably encounter many different kinds of problems. By using a logical procedure, you can face each problem confidently and solve the problem logically and efficiently. Now, this means you need to prepare, to observe, diagnose the problem, and then test the system. Then once you've located the problem, you need to repair it, restore the instrument and the system to service, and finally, document the problem. The amount of time you spend on the different parts of the procedure will depend on the amount of experience you have. The more experienced you are, the more likely you'll be to troubleshoot the problem more quickly. Now here's the work order on that problem with the feed water control system we talked about earlier. Bob, I'd like you to take a look at that feed water control system problem.
Sure. This gauges is fair. I can get back to it later.
Okay, good. Now, in just a minute, we're going to take a look to see how Bob troubleshoots the problem in the feed water control system. But for now, take the time to read the material in your text and have your instructor answer any questions you may have. By now, you should be familiar with the procedure for troubleshooting instrument systems. In the remainder of this program, we'll be looking at an application of this procedure so that you can see the procedure used in practical applications. You'll remember that I've assigned Bob, one of our instrument technicians, to troubleshoot the problem with the feed water control system. As you probably remember, the basic function of the three-element feed water system is to control the amount of feed water flowing to the boiler drum in order to maintain the proper level in the drum. Well, let's join Bob now as he finds out what the problem is and, more important, how he's able to troubleshoot the system.
Well, let's see what the work order says. Here's the description of the problem. It says the feed water flow is reading low and the drum level's a little high. Better take a look at the control logic diagram for the system and refresh my memory on how it works. I know we keep it over here on this shelf. Yeah, let's see. Here it is. This is the diagram of the three-element feed water control system. I had to work on this system a while back. Let me see. How does this thing work? Oh yeah. This system has three transmitters that monitor steam flow, feed water flow, and drum level. The output signals from the steam flow transmitter and the feed water flow transmitters are balanced by this ratio controller, and the resulting signals sent to this feed water controller, where it's balanced against the output signal from the drum level transmitter. The output signal from the feed water controller is sent through a hand auto control station down to a feed water control valve that regulates the amount of feed water that goes to the boiler drum. That's simple enough. Let's see. And this is a flow recorder. It records the value of the feed water flow, and this recorder here makes a record of both the steam flow and the drum level. This is a volume chamber. Its purpose is to delay the signal from the feed water flow transmitter, giving the ratio controller time to respond to the change in steam flow demand. This ensures that the system will be provided with the correct amount of water for the new amount of steam flow. Let's see. Oh yeah, the last time I worked on this system, I wrote this. Feed water flow is greater than or equal to steam flow with system in automatic. Yeah, that takes care of the blowdowns or any small leaks in the system. Well, that's about all I need for now. Time to take a look at the system for myself. Okay, I've got the control logic diagram. Let's see, what else do I need? I need to take my tool pouch and any special tools. Yeah, I should take some leak detector. I don't need any multimeters or any other electronic test equipment. The system's all pneumatic. And this ought to be enough to get me started. With the symptoms identified on the work order, there could be any number of problems. I'll have to go over the problem with the operator and see what he can tell me about how the system's operating now.
When Bob talked to the operator, he found out that the system had been operating under normal conditions when the problem was first noticed. There hadn't been any unusual changes in plant demand for steam, and there hadn't been any equipment failures that would have upset the water level. The operator said the system was controlling in automatic all right. It was just that the drum level and the feed water indications were off. The steam flow indication was okay. The operator said he'd sent somebody up to blow down and check the sight glass on the drum. And the level in the drum was a little high, which agreed with the indication on the recorder. Now, this told Bob that probably both the drum level transmitter and the recorder were working properly. Then Bob and the operator looked at the indicators on the control panel so that Bob could see the indications for himself. The feed water flow recorder showed Bob what the work order had said, that the feed water flow was low. And when he and the operator looked at the steam flow, it was indicating at the normal level. So as far as the transmitters were concerned, the drum level and the steam flow transmitters were probably okay. That left only the feed water flow transmitter as a possible source of the problem. Bob knew from his note on the system that if anything, the feed water flow should have been a little higher than the steam flow. The low feed water flow indication and the high drum level led Bob to think that the feed water flow transmitter could be the cause of the problem. He told the operator that he was going to check out the transmitter and asked him to put the system in manual so he could look it over without affecting the rest of the system.
Yeah, now with the system in manual, I can make a few tests on the transmitter. That's about all I could find out from the operator. Since the steam flow looks like it's okay, but the drum level's off, which the recorder also shows, then it's probably the feed water transmitter that's causing the problem. I better not jump to any conclusions. I'll just look to see what I can find. I remember when I worked on this system the last time that the transmitter's on this panel. I'll put my tools up here, get them out of the way for a minute. Let's see how this thing's connected to the process. Let's see. Gauge. Process pipe runs overhead, and tubing comes down here. This is one root valve, and the line to the transmitter. This is the other root valve, and the line to the other side of the transmitter. See, yes, here's an H. This is my high side, so that makes this the high side valve, the low side valve, and the equalizer. I've got 7 psi output on my transmitter. That matches up with the indication I've got on the recorder. That means that since the recorder is a part of the transmitter's loop, there's nothing wrong with the recorder. It's simply recording the transmitter's output signal. If there's something wrong with the loop, it's got to be with the transmitter. I better take a closer look, see if I can find anything. Well, I don't see anything. There's no signs of leakages. Nothing appears to be damaged or broken. Don't see anything wrong here. Now, this transmitter does have a pneumatic relay. I'll punch out the orifices and see if that affects the signal. If they are plugged, cleaning them will cause the signal to increase. There, that takes care of that one. I'll get this one back here too. Let's see. No, the signal's not changing. Well, there is one check I can make while I'm here in the field. By valving out the transmitter, I can check its output with no input. Close the high side valve first. Now I'll close the low side valve. That's this one over here. Get this valve closed off. Now I open the equalizer. That'll equalize the pressure across the DP cell. With no differential pressure, the output should be 3 psi. Look at that, the output's 0. There is something wrong with this transmitter. So now the question is there a major problem, or is the transmitter just out of adjustment? To check it, I'll need a portable calibrator. That way, I can apply a known input value and check the transmitter's output.
So now, Bob will have to go back to the shop to pick up the calibrator and the necessary tubing he needs to make the checks. He'll also need to call the operator to tell him that there is, in fact, something wrong with the transmitter, and that the operator will have to keep the system in manual until the transmitter's fixed. So far, we've seen Bob observe the system then make a diagnosis that a particular instrument was bad. He was able to test the transmitter by valving it out. And sure enough, the test confirmed to him that there was a problem with the transmitter. So now he'll have to make more tests to figure out what's actually wrong with the transmitter.
I'll have to get this calibrator connected to the transmitter. And get this cover open. See, the first thing I'll do is close off the root valves. That'll isolate the transmitter from the process. So that takes care of the low side. Now I'll get the high side root valve. There. To use this calibrator, I'll have to hook it up to the plant air supply system. I know this panel has a manifold along the bottom of it, and I can connect the calibrator to this air supply. I'll tighten down this fitting. There. And now I'll connect the other end of the tubing to the supply connection for the calibrator. That way I know I'll have an adequate air supply so that I can apply pressures to the transmitter. And I'll just snug this fitting now. Now I'll disconnect the process piping that goes to the transmitter. To do this, I'll need a backup wrench and a tubing wrench to prevent damaging the tubing coupling. I'll do this slowly so that I can bleed off any pressure trapped in the line. A couple more turns ought to take care of it. Now the same for the low side. Screw these nuts off and I can move the tubing out of the way. Now I'll take care of the low side tubing. After I get these connections off, then I'll have to drain the liquid out of the DP cell. In order to be able to check the calibration of this transmitter, I'll have to apply pressure to the high side and vent the low side to atmosphere. If there's any water trapped inside the transmitter, it would cause my input pressures to be inaccurate, and then I couldn't tell whether my output pressures were right or not. I'll go ahead and swing this high pressure tubing out of the way so I can get to the high pressure connection. I'll just loosen this coupling a little and move it out of the way. I'll snug it back up. That'll keep it in place. Okay, now I'm going to have to drain the liquid out of the DP cell itself. It's got plugs here underneath. This is the high pressure side of the DP cell. Before I put this transmitter back in service, I'll have to remember to put some more Teflon tape back on the threads of these plugs. There, that's good. By removing the connections that come from the process to the transmitter, that prevents a vacuum being created inside the DP cell body and holding any water in there. That makes sure I get all the water out of the DP cell so my readings will be accurate. Take care of this low side plug. There, that ought to do it. Now I'll connect this flexible tubing to the calibrator and to the high side of the differential pressure transmitter. With the low side vented to atmospheric pressure, by applying a pressure to the high side, I will create a differential pressure across the DP cell. I need to be certain that I put the calibrator in the vent position to begin with. Turn on the air supply to the calibrator. And my regulator's turned so there's no pressure being applied to the transmitter. Let me see, I've got everything connected correctly. Now I'll switch the calibrator to the pressurized position. Now I can apply 200 inches of pressure to the high side of the differential pressure transmitter. I'll see what its output is with a maximum DP. There. Yeah, look at that. It's nowhere near 15 psi. That's the output it should be producing right now. That'll require more than a calibration adjustment. I'll go ahead and disconnect my calibrator from the transmitter. I'm going to have to take this transmitter back to the shop. There's definitely something wrong in here.
Well, we've seen Bob make his second test. He found out that the transmitter's output was off. So he's been able to locate a probable cause of the problem in the system, the transmitter. In just a minute, we're going to see Bob correct the problem with the transmitter. But before we do, take time to read the material in your text. Do the self-check questions and have your instructor explain anything you don't understand. Up to this point, we've seen how Bob was able to isolate a probable cause of a problem with the feedwater control system to the feedwater flow transmitter. He found that something's wrong with the transmitter that needs to be corrected. Now, as you'll remember, he's taken it back to the shop to check it out. Well, let's join Bob as he tests the transmitter and continues with the troubleshooting procedure. To check out the transmitter, Bob will have to apply known input values and see what the transmitter's output reads. Since this is essentially the same setup that's required in a calibration, you'll need the same kinds of tools. Some pneumatic tubing to connect the instruments, and a means for applying known input values to the transmitter. In checking out the transmitter, Bob's now troubleshooting a specific instrument in the system, not the entire control system. Troubleshooting an instrument is similar to troubleshooting a control system, except that now Bob's got an instrument service manual to help him along.
Yeah, here's a section on troubleshooting. There's a number of checks that I can make. What I need now is a fault correction chart. Let's see, it should be right here. Yeah, troubleshooting. There's a number of procedures in here that I can follow in making checks to the transmitter while I'm trying to find its problem. Here's the fault correction chart. Let's see what it says. Output from booster relay does not increase to about full supply pressure when force beam is pushed towards restoring bellows. Let's see what it says. Supply and output connections to booster relay are incorrect. No, it wouldn't have been working right at any time. Dirty nozzle orifice and booster relay. I punched those out when I was in the field. Vane nozzle relationship incorrect. Now that's a possibility. Let's see what else we've got. Burr on nozzle tip. I'll check that when I look at the nozzle relationship. Nozzle alignment incorrect. That's a possibility too. Let's see. Nozzle airline leaking. All of those things are related to the nozzle. Booster calibration incorrect. No. Vane spring loading incorrect. No, I don't think so. Let me see what else I've got while I'm looking through this chart. Output from booster relay does not drop to zero when force beam is pushed away from restoring beam, causing vane to move away from nozzle. Well, no, it did go to zero, so that's not it. Let's see what else I've got. Output readings are nonlinear. I'll have to check that out when I check the calibration of the transmitter. Leakage from output line or restoring bellows, incorrect vane alignment, dirty nozzle orifice and booster relay. I'll have to check that vane nozzle relationship. It seems to be the most likely problem. To do that, I'm going to have to take the cover off the transmitter. I'll loosen these screws. There. That should do it. Slide this cover off. Let's see what I've got here. The vane nozzle assembly is on this side of the transmitter. There doesn't seem to be any excessive play in the mechanism. I know there's a specific procedure for checking the vane nozzle relationship. looks okay. I'll take a look in the manual to see what the procedure is for checking the nozzle-vane relationship. So it's on page 21. See, the manual says to push the vane close to the nozzle. If the vane-nozzle relationship is okay, they should be parallel with each other. I'll apply a mid-scale pressure so that the transmitter is operating under its normal conditions. Let me see how that relationship looks now. Uh-oh, they're not parallel. Since they're not parallel, that'll keep the error detector in this transmitter from reaching its maximum back pressure. Looked like that nozzle was worn a little bit. I'll see if they have a part number for that nozzle. Let's see, it's back here in the parts list. Yeah, here it is. It's part number 1907204. Yeah, I'll have to see if we've got one of those.
Bob's found out from the service manual that to repair the transmitter, he's got to replace the old nozzle with a new one. But before taking the transmitter apart, he's calling the storeroom to find out whether they've got the part in stock. Now, that's a good idea to keep in mind. It makes it a lot easier to fix an instrument if you wait until you've got the new part in hand. If you disassemble an instrument and then find out that the supply room doesn't have the new part in stock, you could have a box of instrument pieces sitting around for a while, waiting for the new part to arrive.
Dave, I've got to go down to the storeroom and pick up the part for this transmitter. I'll be back in a little while.
Okay, good. Thanks, Bob. Now, when Bob gets back with the new nozzle, he's going to install it in the transmitter. Then he'll have to calibrate the transmitter, making the necessary zero and span adjustments. He'll also have to make the repeatability check. For replacing any major components in an instrument, such as a nozzle and a transmitter, the service manual usually contains the procedure you'll need to calibrate the transmitter correctly. Actually, in fixing the transmitter, Bob will have to first replace the nozzle, then calibrate the transmitter according to the instructions in the service manual. The calibration will consist of applying a known input and then making the necessary zero, span, linearity, and repeatability checks. When he's done, he'll fill out the proper information on the instrument's calibration record, which is usually kept in the shop. And finally, he'll put a calibration sticker on the transmitter. Well, so far we've been able to see Bob locate the problem and find out how to correct it. When he returns, we'll have Bob continue with the troubleshooting procedure. But before we do, read over the material in your text and have your instructor answer any questions you have. Right, I'll talk to you later. Well, we've come pretty far in troubleshooting the problem in the feed water control system. Up to this point, Bob's finished up his calibration procedure. He's replaced the nozzle in the flow transmitter, and, well, now he's ready to restore the system to service.
Now that I got this transmitter fixed, it's time to take it back and reinstall it. First thing I'll have to do is put the transmitter back in place. I'll have to bolt it back on the panel. I'll have to connect all the process lines back to the transmitter and also reconnect and open the supply valve. Tighten down these pressure connections. There. And now for the low side. There, that should do it. All right, now that I've got the connections made, I've got to make sure that these manifold valves are positioned correctly. I want the high side closed and the equalizer open and the low side closed. Now I can open the root valves. I'll open the low side root valve first. And I'll back seat the valve. There. And now the high side. Even though I've opened these valves, there's still no pressure applied to the transmitter. The equalizer's open. I'll slowly open the low side valve, and that will cause the same pressure to be applied across the pressure element of the transmitter. Now, with the pressure applied to both sides of the pressure element, I'll use the vents on the transmitter to bleed off any trapped air. I'll open this vent on the low side first. Let the air out. There, that should do it. Now I've got to do the same for the high side. That vent's back here on the back of the transmitter. There. Okay, now I'm going to close off the low side valve. There. Then I'll do it. The equalizer's still open. Now I'll open the high side valve, and again that'll put pressure across both sides of the DP cell. Now I need to bleed both sides of the DP cell again, just in case there was any air trapped in the high side line. There, that'll take care of the low side, and now the same for the high side. And now there shouldn't be any air trapped inside the DP cell. Okay, the high side valve is open, so I can close my equalizer valve, and I'll slowly open the low side valve. That'll cause a differential pressure to be built up across the DP cell of the transmitter. Now the transmitter should be back in service. I'll see what the output is. 10 psi. That's higher than it was before. I'll just check this connection here at the output tubing. Make sure there's no leak. I don't see any leaks in the process piping either. I'll check back with the operator, have him put this system back in automatic and see how it works.
When Bob talked to the operator to tell him he'd corrected the problem in the feedwater transmitter, he asked the operator to put the system back in automatic to see how the system worked. Then the operator put the system in automatic, and they made a visual check of the system's indications, looking for any problems. With the system restored now, the feedwater flow signal should have increased, causing the control system to bring the drum level back to where it's supposed to be. But when they looked at the indications, they found out that the system still wasn't working right. The feedwater flow indication was okay, but the drum level hadn't changed at all. It was still high.
I tell you what, let's take a look at the diagram. Now, I know that the transmitter is working right because I just calibrated it. So I know that that signal...
Well, apparently Bob was able to fix the problem with the transmitter and restore the system to service. But there's something else wrong with the system that he wasn't aware of before. That just goes to show you that you're never done fixing a problem until you've restored and double-checked everything. Well, in just a few minutes, we'll see how Bob continues. But before we do, read the material in your text and have your instructor answer any questions you have. So far, we've seen a procedure for troubleshooting instrument systems. And we've seen Bob use the procedure in troubleshooting a problem in the feedwater control system. As you remember, Bob was able to locate a problem in the feedwater flow transmitter, repair it, and restore it to service. But when the operator put the system back in automatic, even though the feedwater and steam flow were okay, the drum level indication remained unchanged. Bob knew that the feedwater flow transmitter had to be okay since he'd calibrated it, and the recorder had verified it by indicating an increase in its flow signal. But the fact that the drum level hadn't changed with the system in automatic indicated that there had to be something else wrong with the system.
I'm going to go up and check the drum level.
Okay.
I'll double check the drum level by looking at the sight glass just to make sure the level hasn't changed. The sight glass is over here. No, the level in the sight glass is the same as the level on the recorder. I think I'll head back to the control panel. I'll see if I can use the indications there along with my control logic diagram to figure this problem out. The drum level in the sight glass was just what we've got here on the recorder. Take a look at this diagram. Now what do I know? I know that the feed water flow transmitter is correct because I calibrated, and the drum level transmitter is working properly too. Now both the steam flow signal and the feed water flow signal are fed to this ratio controller, and the signal from the ratio controller goes to the feed water controller, where it causes the feed water control valve to control the flow to the boiler drum. The problem could be with this ratio controller. I want to check that controller out. Can you put the system in manual while I take a look at it?
Okay. You're all set.
Thanks. I think this controller is around here behind this panel. Let's see, here's the doors to the panel. Let's see, the signal from the recorder comes down here through this tubing, comes over here to this controller. FC302, yeah, that's it. Now the other controller's in here too. Let's see. I'll take a look at this controller first. I have to get the cover off. There. I'll just take a look at the thing and see how it looks. And I don't see any problems. Everything looks all right. The setting's where it should be on the proportional band. And the integral setting's right too. I don't see anything obvious. There's no linkages off. Seems to be working all right. I know this controller has a booster relay, just like the transmitter. While I'm here, I'll go ahead and punch the relay out, just to make sure it's working properly. That takes care of that orifice. I can get this one down here too. Now if the signal was going to change, I'd see it on this pressure gauge, but it's staying the same. I'll take a look at my diagram, see if I can figure out what the problem is. I don't think there could be anything really seriously wrong with the controller. After all, it was working all right in automatic to begin with. If the right signal is getting to the feed water controller and the drum level is still not backing off, maybe there's something wrong with the feed water controller itself. I'll have to take a look at it. Let's see, the signal comes from the ratio controller down here, down through here. Yeah, this is the controller right here. I'll get this cover off and take a look at this controller, see if I can see anything wrong with it. There. Everything seems to be in working order. The settings are about where they should be. This controller's got a booster relay too. I'll go ahead and punch the orifices out while I'm here. That's one. Let me get the other. There. Yeah, it's not affecting its output at all. This controller was working in automatic too, just like the ratio controller. You know, if the feed water controller is out of adjustment a bit, it could be receiving the correct signal from the ratio controller, but just be enough out of adjustment so that it won't bring the drum level back down to where it should be. I can check the calibration sticker to see when it was calibrated last. Oh yeah, it's been a while since this controller was calibrated. The controller's output could be high due to some calibration changes with time. To change the output, I'll have to manually adjust or bias the output of this controller. I remember from when I worked on these controllers before, I can adjust the output by making an adjustment to the controller's feedback mechanism. By adjusting the feedback mechanism, I can decrease the controller's output just enough to decrease the feed water flow and return the drum level to set point. And then the ratio controller will return the feed water flow to the proper amount to maintain the drum level at set point. How about putting the system back in automatic for me? I want to see if it works all right in automatic now. Let's see how it's going to work. It's like the feed water flow is dropping off just a little bit. Yeah, that's what it should be doing. Yeah, there it goes. And now the drum level's decreasing just a little bit. There. Looks like it's beginning to stabilize. Good, Mark, I'm going to go back to the shop. I'll check back with you in about half an hour, see if it's working all right.
All right. What you've seen is that a good procedure for troubleshooting instrument systems involves preparing to troubleshoot the system, then observing the system to recognize the symptoms of the problem. Next, diagnose the problem, determine the most probable cause, and then test the system to confirm your diagnosis. Now, once you've located the problem, repair it, and then restore the system to service. And finally, document the problem. By using the procedure each time you troubleshoot, you'll find that you can troubleshoot most problems quickly and efficiently. Take time now to read the material in your text. Go over the self-check questions, and if there's anything you don't understand, have your instructor review the material with you.